Hi everyone, it's Mrs. Griffin with the Unit 4 Lesson 9 video. We're going to be proving we have specific types of quadrilaterals, for example, rhombus, rectangle, or square. So there are 4 ways to prove that something's a rhombus. You're either going to show it's a parallelogram first, which that should be there, and then show it has a special rhombus property that parallelograms don't ordinarily have, like perpendicular diagonals, consecutive sides congruent, or diagonals that bisect the angles. Or you're going to do something and show all 4 sides are congruent to make it a rhombus. We actually don't use this one as much for statement reason or flowchart proofs. We use them more for the coordinate. For the rectangle, you're going to show you have a parallelogram first, and then a special property that's only true in a rectangle style of parallelogram, like it has a right angle or it has congruent diagonals. And then if it's a square, you're showing you have rectangle and rhombus properties that are true together. So it's got to be both to be a square. And here it is spelled out in a different way. So if we're doing our tables, we have parallelogram ACEF, which is here. And we are looking to show that that same parallelogram is also a rhombus. So we have to add in the properties, one of the special rhombus properties. So we also have that AC is congruent to BC, which kind of doesn't really help since they're not together. We have the angle 1 is congruent to angle 2, also kind of a weird thing to give us. I do have a triangle over here. So if angle 1 is congruent to angle 2, that makes it isosceles. And now we can involve another side. We can say that CE and CB are congruent to one another because of that isosceles triangle property. They have 2 congruent sides across from 2 congruent base angles. So EC and BC would be congruent. Since BC was also congruent to AC, it's being used twice, we can use substitution to say that AC would be congruent to CE. Now those are both sides in my parallelogram. Parallelograms normally only have opposite sides congruent, but this one has the ones next to each other. Those are called consecutive sides. So a rhombus is a parallelogram when the consecutive sides are congruent, like here. So we now have a rhombus because our parallelogram doesn't just have opposite sides congruent, it has consecutive sides congruent. Number 2. Now it looks like it could be a triangle proof, and it can be. I'm going to show you a different way to do this though. We have 1 is congruent to 2, 2 is congruent to 3, 3 is congruent to 4, and this is all craziness. What I want to show first is that it's a parallelogram in order to show it's a rhombus. So I'm going to say that I'm going to have parallel lines, because if you look at angle 1 and angle 2, that means that SR and PQ have to be congruent because they're forming that Z shape right here, or parallel. So SR and PQ are going to be parallel. The same thing happens when you look at the fact that 3 and 4 are congruent to one another. 3 and 4 also form that Z shape, and so those are also going to have parallel lines. So parallel lines form congruent alternate interior angles. So we have SR and PQ parallel and SP and RQ parallel. That makes this large shape PQRS a parallelogram because both pairs of opposite sides are parallel. Now, to make it a rhombus, we've got to use an extra specialist property that's not true in normal parallelograms. And that is where I look at my third given I didn't use before. They told me that angle 2 and 3 were congruent. Now that means that SQ is bisecting angle PQR because I got 2 congruent angles. So I have a diagonal that's bisecting one of the angles. When you have a parallelogram whose diagonal is bisecting one of the angles, that's one of the special properties that makes it a rhombus. Number 3. Again, looks like a triangle proof. I'm going to show you a different way. Similar to what we just did. We know angle 1 and angle 2 are congruent. Using that idea like from before, I'm going to use that to say that SR and PQ are parallel to one another. So SR and PQ. I was also told they were congruent to one another from a different given. So because they're both the same sides that are congruent and parallel, that makes this a parallelogram. It has a pair of opposite sides congruent and parallel. Then I'm going to use the 2 is congruent to 3 the same way I did in number 2. I'm going to say that that means that SQ is bisecting angle PQR because an angle bisector divides an angle into 2 congruent angles. And now just like before, if I have a parallelogram whose diagonals bisect the angles, I must have a rhombus. Skipping number 4 because it's intense. Number 5. ABCD, that would be this one, is a parallelogram. We want to show DEFC is a rectangle. Okay, they don't have anything to do with each other, So looking at what we do have, I'm seeing that we have a couple of triangles here. And since they didn't have anything to do with each other in the first place, I'm going to start by trying to prove these two triangles are congruent to one another. So in order to do that, I'm going to focus in on the fact that ABCD is a parallelogram. Okay, if it's a parallelogram, then the opposite sides are going to be congruent, and AD and BC are parts of the triangles, so that's handy. The opposite sides are also parallel, which can come in handy because AD and BC being parallel can lead me towards these angles, their corresponding angles. So I can say that AD and BC are parallel, and therefore angle 1 and angle 2 here would be congruent because parallel lines form congruent corresponding angles. Okay, so angle 1 is congruent to angle 2. Also note I have my perpendicular lines. Don't forget that those form right angles. So angle 3 and angle 4 are congruent right angles. And now if you look at what is marked off for these triangles, I actually have angle, angle, side. And so my triangles are congruent. Now remember my goal was to prove that this was a rectangle. In order to do that, I have to show it's a parallelogram first. So I'm going to use my CPCTC to help me do that. I'm going to use CPCTC from the triangles to talk about how DE is congruent to CF. I'm also going to look back at the fact that angle 3 and angle 4 were congruent. Because if that's true, then here we have congruent corresponding angles again, which means we also have parallel lines again. So DE and CF also have to be parallel to one another. So these two lines, DE and CF, are parallel and they're congruent. Having a pair of opposite sides parallel and congruent makes something a parallelogram. Keep in mind we also knew that angle 4 was a 90-degree angle. And since angle 4 is a 90-degree angle, it's not just a parallelogram, it's a rectangle, because a rectangle is a parallelogram with a right angle. All right, number 6. We have two parallelograms here. Kind of crazy. And they're actually attached to one another, which is weird. And that's all true. But what we're actually trying to prove is that ABCD is a rectangle. So there are ways to do this other than what I'm going to show you, but I'm going to show you the simplest way. If I focus in on the parallelograms, I know that opposite sides of a parallelogram are congruent. So in the yellow one, AB would be congruent to EF, and EF would be congruent to DC. That means that by substitution, if I get rid of the EF, I can talk only about how AB ends up congruent to DC. Okay, I'm going to do something similar with the fact that the opposite sides are parallel. AB would be parallel to EF, and EF would be parallel to DC. Now, it's not substitution because we're not using equals or congruent, but we can say that AB has to be parallel to DC in the end, because lines that are parallel to the same line are parallel. If AB is parallel to EF and EF is parallel to DC, then AB and DC have to be parallel. And now if you look, I have one pair of opposite sides, AB and DC in the green, that's both congruent and parallel. That means that when I have opposite sides congruent and parallel, I have a parallelogram. Now the other given that I was told was that this is a perpendicular here, so this angle 1 here has to be 90 because perpendicular lines form congruent right angles. And what I have is a parallelogram with a right angle, so I must have a rectangle. All right, and the last one I'm going to do for this lesson is here. Number 7, a little bit weird. We're trying to prove that this rectangle is a square. So basically we have that it's a rectangle already. We just need to show that there's a rhombus property that's true too. That's not normally true in a rectangle. So we are told that angle ABX is congruent to angle XBC. that means that there's been a bisect happening here. It means that DB is bisecting angle ABC because an angle bisector divides an angle into two congruent angles. That doesn't normally happen in a rectangle. That's a rhombus property. So if I have a rhombus property in a rectangle, that means I'm dealing with something that's not just a rectangle, but it's also a rhombus, and that's called a square. A square is a rectangle with this rhombus property, the diagonals that bisect the angles. All right, see you in class.